Hi everybody. Now this is going to be a little addendum to the last Electronics 101 and a half that we did, where we talked about DC and AC and how they relate to one another, and we talked about something called RMS value and how useful the RMS of a AC waveform can be when relating it to its equivalent DC. And we looked at how the RMS of a waveform would produce the same amount of heat in a resistor that its DC equivalent would produce. And we actually showed this by doing an experiment. It's very interesting. But it did bring up some very interesting comments from some of you that I thought was worth taking the time to explain in a separate video before we get to our next part, which we're going to look at the power transformer or the voltage transformer of this amplifier. First of all, I kept using the term RMS, and I never really defined what that acronym means. RMS is defined as the root mean squared. And what is root mean squared, you might ask? And I'm going to try to put some things up on the screen here while I'm talking, so you're not just staring at this test equipment. Root mean squared is just what it implies. You are taking the square root of the means squared of a waveform. What on earth is that? Well, that's not so difficult when we're talking about a sine wave. If you do the math, that's where we come up with the 0.707 or the 1.414, and we can go through all that, and we could put that up on the screen here, but without getting too much into it, you can take any waveform, no matter what its shape. So I could take a waveform that looks like this, for instance, and you can convert it to what's called a Fourier series or a Fourier transform. You can actually take a whole series of sine waves, pure sine waves, and if you add those sine waves all together, they will equal, and then connect the dots, they will equal this waveform. And you can do that with any waveform. And if we do math, and if we go FFT, you can see all of the different individual, each one of these little points here equals a sine wave that would represent a part of this bigger waveform here, our main waveform. And if you take all of the amplitudes of all of these little red peaks here, and you add them together, or square each one of them, so times it by itself, add all those numbers together, then divide it by the number of these little peaks we have. You following me? And then take the square root of that, it would give you the average value of this yellow waveform here, which would be the RMS value. I hope that makes sense. Doesn't make sense to me now. I confused myself. Some of you are probably better at putting that into actual grammatical content that makes more sense. But essentially that's what we're doing. And that's what FFT is. Fast Fourier transform. So you're looking at the Fourier series of those individual frequencies that each one represents a sine wave. When added together and you do all that, it will equal this complex waveform. So it's just showing it as a series of harmonics that are all related to one another. Pretty cool how they do that. And that's what we're doing when we're doing the RMS. It's actually looking at this information and calculating it based on this. And the more samples you take, and the further you take the math on this, the more accurate the RMS value will be when it calculates it. So because you're taking a finite amount of samples and so forth, sometimes it may not be absolutely perfect, but it'll be very, very close. And if you look at our meter up here, the stranger the waveform gets, even though this is a true RMS multimeter, and I'm off camera again, the less accurate this is going to be. So you could see these disagree by about 100 millivolts, roughly. 80 millivolts, I should say. But this guy here is probably going to be more accurate because he's probably taking a lot more samples, because this can do 1 gigasample per second. Your meter really isn't doing that. Now, there are much more expensive meters than these that can do a much better job of that, but that's how that works. Now let's look at something else. We're back to our normal sine wave, and it's 60 hertz. So this is similar to what would be coming out of your AC mains, and this is what we were talking about in the last video. And you can see the RMS value on the scope matches the RMS value on the meter. So we see that. But if we add offset to this signal, so now this is now a DC waveform. What? You say? It's a sine wave. It has to be AC. No. DC means the polarity never changes. In other words, here is your ground. Here's your common point. Here's the 0 volt point, is where this little yellow tag is over here. If you notice, it never crosses the 0 or the common point. It never goes negative. The voltage only goes positive. So this is a DC waveform. Now, some people would refer to this as ripple or pulsating. There's different definitions you can use to the type of DC, but since it never alternates, it never changes polarity, it's still a direct current, although it's not a consistent direct current. It is a moving or changing direct current. Now, there's a lot of debate over that. People lose their mind when you say that. Some of them say this is AC, it's offset AC. Well, it would be offset AC if part of this dipped down below. So let me show you an offset AC. Now here is an offset AC. If you take a look, it is AC because it is changing polarity. You see that? So it does go negative, but it doesn't go as far negative as it does positive. And because it's not exactly symmetrical above and below the ground or the common point, we call this an offset AC waveform. But if we take this like that, and it does not go negative, now it is a DC waveform. I hope that makes a little bit of sense. Now, the other thing you'll notice, when we look at our meter here, since this is 4 volts peak to peak, this is still showing the RMS value of AC as being 1.41 volts, roughly. But if you look at our meter, or at our scope, it's calculating it much differently. It's saying that it's 2.38 or almost 2.4 volts. So it's reading differently than, so which one really is the real RMS and why? Well, this is a function of these meters. Whenever you set your meter to AC, the meter disregards any type of offset. It assumes that it is a symmetrical waveform. However, if you look at the scope, it takes into account the offset. So really, RMS is not based on your peak-to-peak voltage. If you remember, it's based on the peak voltage. the maximum voltage that it achieves in either direction. It really doesn't care if it's positive or negative. It just cares how much the maximum peak voltage is in either direction above common. When you look at this one now, since it's offset, your peak voltage is now 4 volts. And your peak-to-peak voltage is 4 volts. So if you look, your peak and your peak-to-peak are the same. Does that make sense? Your peak-to-peak and your peak are the same. And what it's going to do is it's going to calculate RMS. It's going to calculate this as your peak. It's going to look at this waveform for what it is, which is different than a rectified waveform. A rectified waveform does not look like that. Let me show you what a rectified waveform looks like. So just for reference, this is an offset sine wave. So it's a sine wave that does not go negative. It is all positive, so it's direct current. It's not, doesn't reverse polarity. And if we compare that to a rectified AC signal, you can see how they look very different. And if you notice, the RMS value will change between the two. And again, these are two different signals because my signal generator won't drive a bridge rectifier properly. Doesn't have enough output current. So what you're looking at here is my signal generator, which is showing you a representation of an offset AC waveform. And when I move over to the actual mains signal out of a transformer going through a bridge rectifier, so I'll show you that. Here's the transformer, and here's just 4 diodes set up like a bridge rectifier. And this is the output you get. It is not a sine wave anymore. It's a flipped up sine wave. So this is called ripple. And this is 100% ripple. It goes all the way to 0 volts. It goes all the way to the peak. And if we look at it on our meter, this is our true RMS meter once again. You can see it's showing about 6.1 volts RMS AC. Now, the measurement on my scope is not going to be correct because I had to use a special device called a differential probe, so my scaling is off. I would have to change that, and I didn't feel like doing that this morning. But take a look at this. If we go to DC, it actually shows the 12 volts that we have on the transformer minus the voltage drop of the diodes. And we'll get into voltage drop when we do our diode series after the transformer video. So the actual voltage at the coming out of the transformer itself. Okay, let's look at some waveforms. Right now, we're looking at about 14.1 volts RMS. And that is the voltage coming out of the transformer over here. You can see it. And this is a 24 volt center tapped. So you're reading a little bit high. It should be about 12 volts, but because we don't have much of a load on there, and because we have more than 115 volts, we have 125 volts, we're actually getting more than 24 volts out of the transformer. So that's what you're seeing. So there's your 14 volts. And you can see the oscilloscope agrees with the meter. And if we move the meter to DC, it says there's 0 volts because there is no direct current there. It's alternating. Now let's move the probe over here to the output place. All right. Now we're only seeing about 6.1 volts of AC, and this is the output of the bridge rectifier. And if we look up here, once again, if I zoom in, This is reading 12 volts RMS, because once again our meter is not taking into account the offset. So that's showing the non-offsetted. Okay, it's not taking the offset into account, and this one is. But if you look at the waveform, it does not look like that sine wave we were looking at, does it? It's not a perfect sine wave. And if you remember, when we were looking at the offset sine wave, that's what that looks like. Looks very different, doesn't it? And this is a rectified sine wave. See how they're different? Now here's a little more things to confuse you. Riddle me this. Why were we reading about 14.1 volts AC at the input? But now that we have that AC output, why is it reading 12 volts or 12.9 volts? It's actually about a volt and a half less. Well, we're going to learn that on our next video after the transformer video, when we learn about rectifiers. You are actually looking at the voltage drop across the diodes in the rectifier. We'll talk about that later. Just a little primer for later. Anyway, I just wanted to go over a little bit more about RMS, about an offset waveform, and about how those things are calculated by your test equipment. You can see how if you don't understand how your test equipment works, it can throw you off. So just remember, your meter will always take the offset out of the signal, unless you have a meter that's capable of taking that into account. And your oscilloscope, when you're using the measurements, it will actually measure the true peak of the waveform and give you the RMS value based on that. So I hope that makes sense. All right, well, it's time for me to go. So I'm going to get this put together and posted, and I'm going to wish you all peace, joy, happiness, and good health in your lives. We need peace in our world. And I wish you all the best, and we'll see you again on the next video. Take care. Bye-bye.